Yeah, hi. In this video, I want to show you how to do sample inferences about the difference between two means, which means having two dependent samples or two paired samples. So we call them dependent or paired. That's in contrast to the independent samples we did before. So in this case, still, so we have two populations. We sample from the two populations. We have two samples. Now the parameter of interest when we have two populations is the difference between the two populations, which is mu1 minus mu2. In this case, we call it mu d, the mean of the differences. And that's because we're going to be looking at the difference in the data, as I will show you in an example in a minute. So we look at the differences, sample of paired differences data. So this is our data. We need n would be the number of pairs, and we're going to call those differences d1, d2, d3, and their mean is going to be called d bar. The standard deviation will be called sd, and like what's going to go on the right hand side, we call that d0, and alpha is our critical value. So the point estimator for the parameter, which is mu d or mu1 minus mu2, both are the same. You can see here whether I use mu d or mu1 minus mu2 is the same thing. It's going to be d bar, which is the average of the differences, and this point estimator turns out to be unbiased because the mean of the estimator is the same as mu d, which is, again, this is a good property for estimators to have. So the assumptions we need here that we have, or for this method of this section to work, we need normal populations. So our populations we're sampling from are known to be normally distributed. Our samples are small because we still can use it if they were large, but then we can use other methods which are easier to work with. The samples are random. The samples are not independent, they are paired. And so our data is going to be the differences, d1, d2, d3, and so on. And so the sample standard deviation of the sample of n paired differences is going to be SD, and this is from your chapter 1. How do you find the standard deviation? So you take the measurements, you subtract their average, you square. We call these the deviations, and this is the square of the deviations, and that's the sum of square of deviations. Divide that by n minus 1. That gives us the sample variance, and if we take the square root, that gives us the sample standard deviation. So this is what we did in chapter 1. It's the same thing. Also, we want the standard error, which would be take the standard deviation divided by the square root of n. So now we have an estimate for the mean, and we have the standard deviation and n, or the standard error. So we can find the confidence interval. So the confidence interval for mu d would be the point estimate d bar, and since we have small samples, so it's going to be, we use t distribution. We take t alpha over 2. Alpha, our critical value, would be split in half, so we take alpha over 2, and we want the t value for that. And the degrees of freedom here is n minus 1. Unlike independent samples where we used n1 plus n2 minus 2, here we just take n minus 1, the number of pairs minus 1, times the standard error, sigma d bar, or sd over the square root of n. And if we want to make inferences, testing hypothesis, again, mu1 minus mu2 would be d0, or you can say mu d equal d0, and then our upper tail test would be mu d greater than d0, mu d less than d0, or mu d not equal to d0 for two-tail test. The test statistic, since we're dealing with small samples, then it's going to be a t, and remember the test statistic always equals the point estimate, which is d bar, minus what's on the right hand side. Most likely this would be 0, divided by the standard error, which is sd over square root of n. And then we're going to compare this value with the critical value. And so the critical value will be if I have an upper tail test 1, that's going to be if t larger than t alpha n minus 1, I would reject h0. If I have the second test, a lower tail test, I would check to see if t is less than the critical value negative t alpha n minus 1. And these are values we pick from the t table. And if it's a two-tail test, because we combine these two together by taking here t alpha over 2, t alpha over 2, and we want to reject h0 if t is larger than t alpha over 2 or t is less than negative t alpha over 2. And I will show you the graphed decision in this example here and the conclusion. So suppose here we have this example. We have a manufacturer wishes to compare wearing qualities of two different types of tires, say A and B. For the comparison of type A and one type 2, we have randomly, so we take different cars and we randomly assign a type A tire and a type T tire on the same automobiles. So each of the cars we have has one type A tire, one type T tire. The automobiles are then operated for say 1,000 miles, and the amount of wear is recorded on each tire. So that's the amount of wear in millimeters for tire 1 on the first car, 10.5, that's 10.2. For the second one, 9.8, 9.4. For the third one, 12.3, 11.8, and so on. So one thing you notice here, if I were to mount the tires on different cars, so type A tires were mounted in 5 cars, and then type B tires are mounted on 5 other cars, then my samples would be independent, because the amount of wear has a lot of factors to influence it, like driving habits, conditions, weather, and so on. But because I put both tires in each case on the same car, so I have eliminated those causes of wear like driving habit, the condition of the road, and the weather, and so on. So the wear in the tires is completely due to the quality of the tire and not those other external factors. And that's basically what makes those samples dependent. Other examples, like if you look at basically medication before and after a certain condition, and then with the same person. So you'll have a lot of examples in the homework assignments on this to deal with. So in this case, I find the mean here, which is x bar 1, 10.25, and the mean here, x bar 2, 9.76. And you can see here, these are very, very close. So if I were to use the technique we used in the previous section of independent samples, most likely I will see no difference in the amount of wear. But because I have eliminated all other factors, and the difference can only be due to quality of tires, so I eliminated all the noise in the data, so this will most likely show up as a significant difference, and the amount of wear on tire B is less, which means it's the better tire. Let's see. So the above data would have been the sizes of a tumor before treatment and after treatment. So that's another thing. So if you use the size of the tumor before and after treatment, then you can see the samples would be dependent, and then you can judge if the treatment is good or not. So if we were to use, so here if you use the methods of the previous section where we had independent samples, my t statistic would be 0.57, which would be way in the non-rejection region, and I would say both quality of both tires is the same. But let's use the method of this section. So now what we want to do, instead of taking those averages, we are going to take the differences. So 10.6 minus 10.2 is 0.4. That's my D1. 9.8 minus 9.4, that's 0.4 D2. That's 0.5 D3, D4, and D5. And you notice that all these values are positive. So in all cases, this tire had more wear than this tire. So I find the average D bar would be 0.48, and then I can find the standard deviation using the formula I gave you above, or you just use your Excel using this formula from chapter 1 or 2, or the shortcut version of it. So we can find SD, and you should do this to make sure you can find the standard deviation, which would be 0.0837. You can see we have very small standard deviation. Now, do the data provide sufficient evidence to indicate a difference in the average wear for the two tire types? So the testing hypothesis here is my mu d, which is mu1 minus mu2. Remember, this is my unknown parameter. Is this 0 or not 0? If it's not 0, that means the tire's amount of wear is different for all cars, not for just the 5 tires we tested. But based on the 5 samples we tested, we can calculate T now. D bar minus D0 over ST divided by the square root of N. So that's 0.48 minus 0. My standard deviation is 0.0837, and that's square root of 5. So if I do this calculation, that's 12.5, and that's a very large T value. You can see if we were to use independent samples, our T value was 0.57, the incorrect one. The correct one is 12.8. Shows a big difference. So now let's graph this and see what would be our test. So in this case, I would have a T distribution. This is my T distribution. Okay. And I want my T value. What's my critical value in this case? It's going to be T alpha over 2, and the degrees of freedom are going to be 5 minus 1. So let's see, what did we use for what did we use for alpha? Well, alpha is, we used an alpha of 0.05, so that's 0.0254, which is 2.776. Okay, so our alpha is our T value here is 2.776, and that's because we used alpha is 0.025, so 5 divided by 2 and 4 degrees of freedom. So we check that in the T table, and we find that to be equal to this value. So this is our value here, 2.776, and because it's a two-tail, I'm going to have another value here, negative 2.776, and so my rejection region would be up there or down here. So whether if I have a very large value or very small value, I would reject, and otherwise I wouldn't. So my value was way up here, 12 point, what was that value? 12.8. Okay, so 12.8 here, so it's way up in the rejection region, and my decision would be to reject H0. Okay, so we reject H0. So what does that mean? Let's go back to the handout. So we reject if t is more than the critical value or less than the negative of the critical value. And so we reject H0. That means at 5% significance level, we have sufficient statistical evidence to indicate that the amount of wear or for type A tire is not the same as type 2 to type B tire. Okay. So we conclude they are different. And as an exercise, should construct a 99% confidence interval for mu d. Okay, see if you can do that, and hope this helps. Take care.